In our lithium-ion batteries, we have, it's very simple. There's an anode, there's a cathode, and there's a separator. The separator has electrolytes. Let me mention about the electrolyte first, because what's in our commercial batteries are liquid electrolytes. These liquid electrolytes are organic, and invariably all the bad press that you hear, all the fires, invariably are from this reason, from the electrolyte burning for one reason or another. There could be a short circuit or something, or maybe there was just no voltage cutoff. But in any event, liquid electrolytes. So that when we talk about the future, and I'll talk about this very briefly, this will be replaced by a solid electrolyte. It's not going to be tomorrow. It's not going to be in the next 5 years. But it will be a little bit in the next 5 years. But beyond that, we need major significant advances in areas of interfaces between the electrode and the electrolyte. In the case of liquid electrolytes, it's not such a problem, or at least it's controllable. Then you have the anode material. Typically, this is graphite, one reason being financial, but also it works extremely well. And the other is a cathode material. And as I'm about to show you, the cathodes are what really, truly limits the energy storage capabilities of lithium-ion batteries. On the right-hand side are some of the more common materials that are used. Lithium cobalt oxide is a cathode material. Its layered structure promotes the lithium-ion insertion and deinsertion as needed. You have also vanadium oxide. This is a zero gel material, and so now the same kind of process occurs there. You do not necessarily need to have two-dimensional materials. You can do very nicely with one-dimensional materials. Lithium iron phosphate, which is a derivative of the olivine structure, has channels where lithium ions go in and out. And all of these have, for the most part, rapid ion transport, but there's limitations on that, and that's what I'm going to talk about. The cathode I mentioned is what is limiting energy density in lithium-ion batteries. This is a nice plot that shows you the voltage or the potential that's all referenced to lithium, and then over here you have the capacity, which is really the energy density. Down here are the materials which we call anodes. The fact that the electrochemical community calls them negative electrodes, just consider the electrochemical community a little, okay. All right, some of my best friends. And in any event, you have over here the positive electrode materials, and those we call cathode materials. And you can see very rapidly that there are a number of materials that have very, very good energy storage that are down here that are the anode materials. Over here, you can see limitations. These days, there's a lot of work on trying to extend this, and certainly to make them safe as well at the same time. But for the most part, getting to something on the order of 250, we'll call that milliamp hours per gram, is a chore. And for the most part, everything commercial that you have is roughly half of that. So there's quite a bit of room to grow here. Some recent developments in the area of lithium-ion batteries, which I should say, you see kind of an improvement about a factor of 2 about every decade. So it's nowhere close to what you see from Moore's law. But in any event, there's been some advantages in the past few years related to nanomaterials. With nanomaterials, what you're able to do is to decrease the path of the ions, which means the transit time gets shorter. And if the transit time gets shorter, it means the power goes up. You also improve electron transport. So for the most part then, what happens is that you are able to retain relatively high capacity at high current density. And that's a good thing. That's high power, and you're also retaining some of this high energy density. Another, from a more scientific feature, but something that you know is going to pay off in the future, is the fact that when you go to nanoscale, you now enable reactions that you often cannot have otherwise. And a perfectly good example of that is what we call conversion reactions, where you take a material, an oxide, which is not electrochemically active, but when you react it with lithium, so thermodynamically it wants to react, then what will happen is that you can now form nanoparticles, and these nanoparticles can operate very nicely and now give you high energy density over 1,000 milliamp hours per gram. This works extremely well for anode materials. We've got a lot of those. It doesn't work so well for cathode materials, but again, that's a great area for the future. Another area for nanomaterials has been what we call core shell morphology. The limitation in a lot of the cathode materials in lithium-ion batteries is that they are wide bandgap semiconductors. They do not transport electrons very well, and so you need to help them in some fashion. And by going to core shell type structures, as you see here very nicely, you are able to very well get electron transport in combination with the ion transport that the material in the center would be using. Lithium iron phosphate is perhaps the best example of this. This material is really insulating, but when you put, actually all you have to do is react sucrose in an atmosphere where you have some pyrolysis occurring, then you get a thin shell of carbon, and the material now gives you very good characteristics here of the discharge characteristics of the material at various energy densities. And so this works out very nicely. You can also work with conducting polymers and so forth. Core shell morphology has been a big boon to this field. And then finally, with lithium-ion batteries, you can always talk about new materials. I talk about this as the great rock hunt. It's not really quite that way. The field these days is going towards what we call framework structures. These are phosphates and silicates and sulfates for that matter. You could see that their energy densities are not that great. They're on the order of maybe 150, at most 200 milliamp hours per gram. We would love to make that a factor of 2 higher. But in any event, these are considered to be low-cost materials, safe materials. And again, these are very insulating materials, and so you have to use core shell morphology.